Hi, this is Snwadi. In this video, I'm going to demonstrate to you how we can construct a model for the proof of Schröder-Bernstein theorem. Schröder-Bernstein theorem, or sometimes called the Cantor-Schröder-Bernstein theorem, is one of the most important theorems in fundamental set theory. It is stated like this. If a set A has cardinality less than or equal to B, and B has cardinality less than or equal to A, then we know that A and B have the same cardinality. In other words, they are equinumerous. From the given conditions, we know that there is a function f from A to B that is 1 to 1. There is also another function g from B to A that is 1 to 1. Our goal is to find another function h from A to B that is bijective. In other words, it is both 1 to 1 and onto the set B. This theory obviously applies to the finite case, since in that case, either f or g can be the suitable function h. But for the infinite case, f and g might not be bijective, so we need to construct another function h. Since we only have knowledge on the function f and g, I will now show you how to construct a suitable h from f and g only. For the ease of demonstration, let us see an example. Let the set A be the natural number set, and the set B be the set of all even natural numbers. Let us define f as fx equals 4x and g as gx equals x. Obviously, we can see that neither f nor g is bijective because neither of them is onto the codomain. The general idea of our construction is to make h a mixture of f and g. In other words, for some elements from A, we have hx equals fx. For the other elements, we define hx as the inverse of gx. Another idea, which is sometimes called procrastination, is that we only assign either f or g inverse to h when we are forced to do so. Let us check the image of A under f first. Since fx equals 4x, the image of A will be all the elements from B that are multiples of 4. So we know that all the elements from B that are not multiples of 4 cannot be mapped onto using the function f. This means that we are forced to use the function g inverse to map to these elements. The red arrow here represents the mapping of these elements under G. Since G inverse is the only way to map to these elements, the red arrows are actually finalized as part of our function h. We notice that once the red arrows are finalized, some new elements from set A cannot be used to define the function h. They are 2, 6, 10, and all those numbers that equals 2 modulo 4. We have to remove the mapping under f on the set of these elements. Once we have done so, we find again that there are some new elements from the set B that cannot be reached under the function f, meaning that we have to use G inverse to define h that map to such elements. So let us repeat the process. We add some new red arrows to our finalized function h, and this will result in some new elements from the set A to be occupied. We then remove our mapping of these new elements under f, and this will cause some new elements in the set B to be unreachable under f. Similarly, we have to use the function g inverse to map to these elements. and the rest of the construction is simply to repeat this process till infinity. We notice that there are some elements in the set B that are never reached under the red arrows, which is our function h. For example, the element 0, 4, 12, and so on are never reached. In this case, to ensure that our function h is on to B, we simply need to define these elements under the function f. Note that the elements from A that is mapped to any of these elements in B under f must have not been occupied yet, because if some of them are occupied, for example, let's say an element alpha from A has been occupied, then following our earlier algorithm, since f alpha is unreachable, we would use the function G inverse to define the mapping towards f alpha. Then the element f alpha would have been reached, which contradicts our condition that it is never reached even if we have repeated our algorithm till infinity. Therefore, we have constructed a function h from A to B that is both one-to-one and onto B. This proves by construction that there is a bijective function from A to B, and hence A and B are equinumerous. The Schröder Bernstein theorem is true.